Welcome to the fourth part in this series where I will be sharing my attempt at building a self-driving RC car. In the last video, we got ourselves a brand new Raspberry Pi 5 for deployment, as well as a Raspberry Pi Zero 2 for prototyping our setups. Well, ladies and gentlemen, the parts are finally here. Why do we need the Pi Zero, you may ask? Well, in case something goes wrong, for example, I make a wrong connection and it fries, or my neighbor's cat decides to steal it, it will not matter as much because a new Pi Zero costs only like $20. Anyway, now what we want to do is to make wirings such that we can both control the car as well as monitor the PWM values that our transmitter sends to the Pi at the same time. By tracking this data, we can eventually create training data for a machine learning model to learn to drive. Our data will consist of time steps for which we have channel 1 and channel 2 values, along with a matrix representation of the current frame obtained by our camera. We are going to show our model a bunch of these frames, for which it will learn to come up with optimal channel 1 and channel 2, that is, steering and throttle values. I got started by flashing the SD card with Raspberry Pi OS, which consists of setting up an internet connection, password, and things like that. Then I plugged the card into our Pi. Next, I tapped into the channel 1 and channel 2 ports of the receiver using our new Pi Zero. The PWM values go straight into the GPIO pins that you can see on the Pi. I had prepared the wiring setup while I was waiting for the two Pis to arrive, and of course it worked flawlessly on the first try. Better safe than sorry, right? We can now hear the car's tires turning while we are similarly receiving data. This is exactly what we wanted. Now that we have confirmed our setup is safe, it is finally time to unbox the beast himself, that is, Raspberry Pi 5. Compared to the Raspberry Pi 4 Model B, this little board is a serious leap in speed. The Pi 4 was no slouch, but its quad-core Cortex A72 processor at 1.5 GHz has been replaced by a quad-core Cortex A72 running at 2.4 GHz, bringing both higher clock speeds and more modern architecture for faster, smoother performance. This new Pi requires an adapter cable to connect to the 15-pin Raspberry Pi camera module 3. Replacing the old cable was easy, now we just had to attach the cable to our Pi. It locks inside these pins, right next to the Ethernet port. And boom, we're done installing the camera, as you can see here. Next, I replicated our earlier wiring setup that we tested with the Pi Zero. It was quite easy to do, as I just had to move the GPIO pin connections to our Pi 5. Then I ran some updates and tested the camera. And it worked on the first try. Now we should be able to run our data collection setup, where we are able to both control the car and collect our PMW values along with camera footage. To make this work, I wipe-coded two Python programs called monitorchannel-save.py and recordvideo.py. The first program continuously logs the PMW values, while the second captures and stores the camera feed. To launch them as simultaneously as possible, I created a third file named supervisor.py. It fires up both the video recording and the PMW logger at nearly the same moment, producing two files, a CSV file containing the PMW data and an MP4 containing the video footage. So here we are after transferring these files to my main computer. The PMW data looks like this, so we have the timestamp and the values themselves. In another file, we have the timestamps for the video. We know that the supervisor.py file that I showed you cannot execute both programs at the same exact time. But for our purposes, it is extremely critical that we are able to accurately align each frame with its respective channel 1 and channel 2 values, because that is the nature of our training process. Lastly, we have the video file, which is just footage of me waving my hand. To put everything together, we have a post-processing Python script that reads the timestamps and aligns the data. This step guarantees that every frame of the video is paired with the correct PMW values, giving us perfectly synchronized data for training. It starts with loading in all 3 files. Then we get the exact moment our video started by picking the first value from videotimestamps.csv and find the matching channel 1 and channel 2 values from pmwlog.csv, store them together, and move on to the next time step. To confirm the post-processing program works as intended, I have edited 4 of the video's frames to contain a piece of text. I know that these are the exact frames containing the texts, and if we take a look at the frames, they should be visible. We can see the previous frame before our first target frame, the target frame itself, and the next frame, which in this case also happens to be a target frame. By continuing to go through the samples, we can confirm that our program does exactly what we wanted. Once the Waveshare power supply module I have ordered arrives, we will be able to run the Pi without being tethered to a wall. That will let us record driving footage and verify that the PMW values are perfectly synchronized with each frame. Thank you so much for watching, and I will see you in the next video. Peace!